The AC generator. A simple AC generator consists of a coil of wire which is rotated inside a magnetic field. It's simpler if we look at this in two dimensions, so here we're looking end on, and this down here would be looking along this part of the coil. So the coil would rotate something like this. Looking in more detail at the motion of the coil, in this position the ends of the coil would be moving like this, and in the extreme vertical position, as shown here, there would be a minimum field line cutting. The ends of the coil are moving parallel to the magnetic field lines at this point, so the EMF induced would be 0 volts. In this position, the ends of the coil would now be moving like this, perpendicular to the field lines when the coil is in this horizontal position. So there would be maximum field line cutting, and the EMF induced in each side of the coil would be given by BLV, where B is the magnetic flux density, L the length of the side of the coil, and V the speed at which it moves through the magnetic field. So the maximum EMF induced in the whole coil, which I'll denote as epsilon naught, not to be confused with the permittivity of free space, will be equal to 2 BLV, as there are two sides to the coil, this side and this side. If there are n coils of wire, this will become 2n BLV. But the speed v is equal to r omega, where the radius of the circular orbit is half the width of the coil, here w. So we get that the speed is equal to width over 2 times omega. But the width multiplied by the length of the coil gives its cross-sectional area. So we get that the maximum EMF epsilon naught is equal to nBA omega. If we plot a graph of the EMF induced against time for one complete rotation of the coil, we'll start with it in this position. Here I've coloured it grey on one half and black on the other, just so we can see the rotation of the coil in all positions. Now in this position, the ends of the coil are moving parallel to the field, so there will be 0 EMF induced. In this position, the coil produces the maximum EMF, and I'll call this a positive value up here. Another quarter rotation brings us to here, and now again the ends of the coil are moving parallel to the field and no EMF is induced. Now the ends of the coil are moving in the opposite direction to what they were here, so the grey side here is moving up, whereas here it was moving down. So the EMF will be in the opposite direction, but again will be a maximum down here somewhere. And finally back to where we started from with 0 EMF. So now we can join these points with a smooth curve. In fact, it can be shown that for a coil starting at the 0 volts position and rotating with a frequency f, that the EMF induced at time t is given by the maximum EMF times the sine of 2 pi times the frequency times the time t. But we found previously that epsilon naught equaled nBA omega, and so we get this expression. But for frequency is equal to the angular velocity omega over 2 pi, so we can then write this expression. Let's look at an example. A rectangular coil of side length 5 cm and width 3 cm has 50 turns of wire and rotates in a uniform magnetic field of 50 millitesla at a frequency of 200 Hz. Calculate the peak EMF induced. Well, for this we can use this expression, but at the peak, sine omega t will equal 1. So we can simplify this to the EMF is equal to nBA omega. Also, omega is equal to 2 pi f, so we can write the EMF is equal to nBA times 2 pi f. All that remains is to put the values in, and we get an EMF of 4.7 volts. Next we're asked to calculate the EMF 1/8 of the time period after the start. Well, first we need to find out what the time period is, and it's given by 1 over frequency, which in this case is 1 over 200 Hz, giving a time period of 5 milliseconds. So 1/8 of this is 6.25 times 10 to the minus 4 seconds. Now we need to make sure our calculator is in radians. Before we carry out this calculation, we can now put in all the values we have, and this gives an EMF of 3.3 volts.